Advanced Scala. So one thing I would like to tell you is that my presentation will be mostly about features which are mostly used for building libraries or reusable code in Scala. The reason as an application developer you should care about them is mostly to, let's say, to debug your code, to understand compilation errors and stuff like that. But yeah, probably at some point you will also start writing some reusable code, and well, you can learn these features one by one. Like, there are really lots of features which are kind of optional. Like in C++, you don't have to use all the features out there, but you can, and you will slowly learn them. And so, basically, as an application developer, these are typical features which you will be using. So I will not read them to you, but there is beginner level, intermediate, and expert. And after the previous great presentation, you are roughly between A2 and A3. Congratulations. You made it. And so the library developer is, there's a bunch of more complicated and abstract things used for mostly library development. Again, I will not read them to you. I will show many of these features today, mostly as examples, because otherwise you would fall asleep. And let's see what we have. So just to remind you, the syntax for higher order functions. Who knows what's a higher order function? Yay. Then I don't have to explain it to you, but basically higher order functions, they take or return functions as arguments. And surprise, surprise, this is the syntax for functions, function types in Scala. So that's a parameter type, that's a return type. And if you have two parameters, well, here you are. And just to remind you, these are the type parameters. So, well, actually, Chad mentioned this function. I just wanted to make sure you know their signatures. I will not read them to you, but hopefully you can understand. How many people can actually understand these signatures? Yay, good. So one small but very nice feature is that something called call by name parameters. So if you write a function which doesn't have any parameters here, so basically it's a function which kind of stupid, right? There is nothing here. Then when you call it, this run later, this block is not executed before you call this run later. Instead, you get basically a closure. Who knows what's a closure? Yay. So this f will be executed only when you reference it inside this function. So, well, basically what you can do is it's a run later, blocking expensive function, start a thread with a runnable, yada yada. Here you actually run the function result, and then you, well, do something with the result. And, well, yeah, we will use this code further. The only thing I wanted to basically point your attention to is that we can have this call by name parameters, well, without any arguments. Why is it cool? Well, you can basically write things which kind of extend your language. You essentially can create new statements like if and so on. So now in Scala there is a whole world of implicits, and that's a compile time feature which on one spectrum allows you to monkey patch your code, and on the other spectrum allows you to do very complicated computations at compile time. Somewhere in between there are reasonable uses of this approach, and they really allow you just to write much more nicer code. So a very simple example is that, so suppose we have a value of type A, but we use it somewhere which kind of wants it to use it as type B. And so if you look at this object here, so that's basically a static method, quote, quote. And we have a method which is like, it takes A type as an argument and returns B. And it's marked as implicit. So if such method is imported into the static scope of this declaration here, the compiler at the compile time will replace A with this. Now, if you use it for very standard types like integer or string, your life will be very sad. But if you do it for your very specialized custom types, you can basically save for your library users some typing effort, because there will be some automatic conversions between types. Again, use it sparingly, but it has its places and uses. and it happens in compile time. All right. So extension methods. So, well, that looks strange, right? So I don't think 5 has a method seconds. It's an integer. So what happens here is that we can define an implicit class, which constructor takes one argument of type integer, and it has a method seconds. And because when compiler sees this method, and this thing is in the static compiler scope of this expression, the compiler will replace it with, well, this expression, right? So it creates new duration int, which is this class, and, well, calls the seconds. Again, it looks like monkey patching, but it actually can be pretty nice in some contexts. Apparently, another popular name for this approach is pimp my class. So that's actually the author of Scala calls it this way. So he has interesting sense of humor. All right. Implicit parameters. Well, this is really useful feature. So what happens is that I can define a method with 2 sets of parameters, or more actually. And one of the parameters, or many of them, can be marked implicit. Now what it means is that on one hand, I can really just call work, and then I can just say, let's say that's the first set of parameters, and then explicitly pass the second parameter. But if I don't pass explicitly the second set of parameter, but there is such declaration of the type of the implicit parameter, the compiler will basically replace this code with this code. Well, you will just have to trust me that it's a very useful feature. It's not just monkey patching your code. So here is actually an example why it's a useful feature. So what I'm trying to achieve here is something called type classes or ad hoc polymorphism, which is basically monkey patching your classes to fit some other function. So what we do here, we want to write a function minimum which works with any kind of type. And obviously all types don't have a compare function. Well, we have this generic function in type t. It has 2 parameters, a and b of type t. And now what we ask is for implicit parameter of type ordering t, right? So for instance, here I have a function called min of 5 and 6. And if for some magical reason in this statical context there is an object of type ordering int, then everything will magically work. And well, here is the magic. It's an implicit object, int ordering, which is of type, or extending the trait ordering int, and it has this magic compare method. And voila, we now can have basically, we can take any type and monkey patch it into, well, having a compare method. Very powerful concept. So for instance, Haskell has type classes as a main construct. It's like one of the main features. There is also a paper which shows you that everything is possible, can be done with implicits. We will not talk about it, but anyways. So just, yeah, to explain you the syntax, so that's the syntax I showed you, right? So minimum of type parameterized by t of a and b with implicit ordering, right? That's what I showed you. So there is a shorthand which basically does the same thing. You can write t colon ordering, and the compiler will just replace this with that. So there is no deep reason, it's just easy to read this way for some people. Yeah, there is this also magic function implicitly. Well, given that I don't have this O anymore here, right? So basically this implicitly ordering t is equivalent of this O. It's just an implementation detail. But it can be very useful in some contexts. So far, was it clear? All right. Did anybody learn anything new? Good, good. Annika knows everything. Features. So actually, I'm pretty sure that most of you know what a feature is, right? Do you know what the promise is? Okay. So I really just want to show you this stuff mostly because of Scala syntax and because it introduces some additional Scala concepts in the examples. And then we'll look deeper into the Scala concepts. So future is a way to asynchronously retrieve a result of concurrent operation. So we have a future with some blocking expansive function returning a value of type result. So in Scala, you can annotate any expression with a type, obviously. And now the interesting stuff happens later. So futures run in some execution context. Execution context is just basically a thread pool. It's an abstraction to run runnables. And it actually expects it to get as an implicit parameter. Again, well, it's not very interesting per se. Now, another thing you shouldn't do is you can synchronously await on futures. You can write await result future, 15 seconds. And it will wait for 15 seconds to get the result. Otherwise, you get an exception. But frankly, you should not be doing that. And more nice way is to use callbacks, in this particular case, on complete callback. And there are two cases, either the future succeeded, and that's the result here, right? Or the second is like there was an exception, and then you have to handle it. Again, it's very basic stuff. Please don't fall asleep, it will get more fun. So what a promise is. Promise is a way to communicate values between threads in a functional way without some scary synchronized blocks and so on. So that's an interface, a promise of result type R. So it has essentially two methods. First, you create a promise, then you can ask for a future of this promise, which is not complete yet. And then later on another thread, you can say that this promise has succeeded. I am fulfilling my promise and giving you the result R. And now if this original thread who created the promise or has the future waits for this future, it will get this result R. So you first create a promise and you create a future. On another thread, you, well, tell the promise that you succeeded, and then on the original thread, you get the result of the future. Did anybody understand what I just said? Yay. Beer doesn't work. It was alcohol-free beer anyway, so. And so, yeah, so here is actually the code I showed you on the first slide, but now with promises. So here is this run later function. So what it does, it creates a promise, creates a thread, takes the result of this call by name function, says promise success result, and well, by that time your result future will complete and you will get the result. Nice and easy. So futures can be composed using callback hell. So if you have a future or 5 futures and you want to wait for them, and when they complete, you can do something next in another future, and then again and again and again, your code will get very ugly. And this is really a really simple case. So I don't suggest you read it, but it doesn't look very nice, right? And so what saves you is a monad nirvana. So I will spend very big chunk of my presentation telling you about all this stuff. But before I do that, how many people here know the 4 comprehensions in Scala? Yay, and who knows what a monad is? Wow. Anyways, so just bear with me. It's just imagined as a nice syntax for something. So I first created 2 futures for querying 2 exchange rates, right? And they are already running asynchronously. I'm not waiting for them. And now what I do is I basically write, give me dollar exchange rate, franc exchange rate, check if it's profitable, and buy it if it is. And I claim that the result of this expression is a future. And when it completes, you say, I purchased this amount. So, and that's a very powerful concept, because you can use it with very many different types. And we will talk a lot about that. So, that's the code block, right? I'm trying to explain what happens to this code block. So this code block on the next slide is at the top, and it's basically the compiler using the holy trinity of Scala translates it into the, well, let's say just invocations of functions, methods of the future. So you have this USD code future. It actually has also a method flatMap, which kind of is similar to what list had, if you remember. And then, well, there is something called withFilter, and then there is also method map, which again is kind of suspiciously like list. Yes, the guy in the blue shirt. He's completely not a place duck. He is not working at PlanetOS. There is no relationship between us. So this is the Father, the Son, and the Holy Spirit. So this is Marcin Odersky, Scala, and category theory. All right, and these are not unicorns. These are unicows, just to be clear. For comprehensions. So for comprehensions work with any type, which is a monad. And here are some simple examples of monads, but actually there are also very, very complicated kinds of monads. And well, one of the simplest kinds of monads is a list or a sequence. So sequence is a supertype of list, but just imagine it's a list, but technically it's a sequence. So what happens here, it's a very, very fancy for loop. So I iterate from 0 to 100, and get I. Then I iterate from I to 2 times I and get j. And then I do some test on that, and then I yield these pairs of I and j which match these conditions. And so I think most of the languages now, okay, good languages, not Java, right, have for comprehensions like Python, but I think also, yeah, Python anyway. Now most functional programming languages, or at least which pretend to be functional, have it. But in real functional programming languages, it works with very many different kinds of types, which are monads. And so, more interesting example is that option is also a monad. If you remember, Chad actually showed you that option has this magic method flatMap instead of map. But what happens here, so just for the fun of it, here is the definition of the option. So we have a trait option. You can safely ignore this plus t. So plus is basically a variance annotation for people who know that. But yeah, it's just a trait, right? Basically an empty trait parameterized by t. And the sealed means that all subclasses of this trait are given in the same file. Why it's good is because if you do pattern matching on options, the compiler can check that you have a case expression for all options. So if you forgot to match on none, the compiler will tell you that you've been naughty, and probably you'll have a bug there, which apparently helps people save lots of, well, money by not making this bug. So that's actually very often how the equivalent of null pointer exceptions are caught in Scala at the compile time, because none is kind of null, and the compiler will tell you that, you know, something is wrong. So what happens here is that we have two functions, and they actually both return option, right? So they might return a result, which is a sum, but they might not return a result. And now the trick is that when they return a result, then the next function is called, right? With, sorry, that should be I, by the way. And then if that returns sum, we go here. But if here we get a none, then this whole thing finishes and you just get a none. And if this thing gives you a none, then the whole thing finishes and you just get a none here. And I think it's kind of nice. Did you understand what I just said? Cool. So, for comprehensions. So for comprehensions is a syntactic sugar for view methods. So in the simplest case, if you have such for expression, then the yield becomes the map function. So, well, you have yield f of a. Here you have map f and a. Very easy. A more complicated case where you have, well, two of these generators, right? In this case, basically, this arrow becomes a flat map. And then the yield becomes the map inside this flat map. So again, pretty easy, right? And if you have a check, it becomes a with filter. And the idea is that basically if your type has these three methods, map, flat map, and with filter, and one more, which I will show you later, then you can use it in a for comprehension. And so there are really many different examples of monads. So the simple ones I just showed you, like sequence, lists, options, either, try. So try is actually a thing which either, it's like option, but the none, instead of none, you have exception information, right? So basically it tells you when the first time was when it failed. Futures I already showed you, so futures can be used in for comprehensions. So in the real functional programming languages, which don't have side effects at all side effects, like Haskell, are encoded using IO monad. So the only way to make side effects is, well, you will have to use the for comprehension, which is called do notation in Haskell, to basically, well, encode your side effects in the monad, IO monad. And actually, like really people who maybe have programmed in Scala too much for their own good, they start encoding the side effects or specific effects of their code in monads. The problem is that usually people sitting next to them don't understand their code, but that's the next problem. But if they have 10 people who all understand this stuff, you can be super efficient. So more interestingly, like Scala generally is meant for all kinds of domain-specific languages, and so libraries, frameworks, and to do it so that for a user, application developer, the syntax is very nice. And so here are a couple of examples of monads, which is not the only way to do libraries, but one of them, I will show them to you. So query DSL. So there is something called SLIC, which is a functional relational mapping, like Java has object relational mapping. And well, hopefully you all recognize SQL, right? Well, surprise, surprise, you can encode it pretty much with exactly the same syntax in for comprehension. And as far as I know, I don't know C#, but I think C# is basically exactly doing the same thing in Linku. So, surprise, surprise, I think probably this is also a monad. I have to think about it, but that's a monad definitely. So I have to admit that the downside of SLIC in particular is that if your program doesn't compile, you will probably tear out some here from your head to understand the compiler error messages. So for those people who have tried C++, some very advanced template libraries, and something doesn't compile, you will get one page of template compilation errors, and then you will have to work for compiler yourself for half an hour. It can happen, but you will learn how to handle it and how to live with it, similar to C++. So, you know, nothing is perfect. And maybe someday they will write language with A, cool type system, and B, readable error messages, but it hasn't happened yet. And Scala Check. So a very powerful concept from, again, actually Haskell. They have a quick check. Scala has Scala Check. So if you have a bunch of code which is functional, it doesn't have side effects, it's very nice to test it because it doesn't have any variables. You can like run it on many threads on one thread. You can restart it as many times as you want. And so the idea of Scala Check is that you generate a bunch of random inputs to your function, and then you specify properties which your function result must satisfy. And you can, in this particular case, use for comprehensions to specify what kinds of random inputs to generate. So, for instance, this thing here generates your randomly structured trees with leaves containing integers. Like, you don't have to understand all the syntax, but here it says that, you know, please generate an integer from -100 to 100. Here it generates leaves with integers, right? And here it generates nodes. And the whole thing, well, is one-off, leaf or node. And the result is that this thing can actually generate your random trees with integers in the leaves. So this way you can very efficiently create unit tests for your code, but it probably means your code should not have side effects, or at least they should be inside your function. So like if you do have variables inside your function, but you don't modify any external variables, okay, like maybe there will be more bugs, but you can use it. But if there is some external mutable state, well, you will have to probably mock it or something. But really, like in the domain where Scala is very good, which is typically data processing, web requests actually also, and the writing compilers, especially Scala is the best language for writing Scala compilers. Actually, Haskell is the best language for writing Haskell compilers, but I think it also applies to Scala. So yeah, immutability really helps in these domains. So if you're writing user interface or a low memory embedded system, then yeah, probably it's not the right place. Although people have tried writing user interfaces with completely functional approach where there are no variables, but I think this bright future hasn't arrived yet. Yeah. So to quote one famous contemporary philosopher, monads, 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 monads. So what's a monad? Monad is just a monoid in the category of n-functors of X with products replaced by composition of n-functors and units set by the identity n-functor. I actually recognize some of the words here, but unfortunately not all of them. Someday I will reach the enlightenment. So on a more serious note, so I have to admit that the top part of this slide is also written to sound smart. You can ignore it, but basically, essentially, that's what the monad is, right? So monad is, let's say, a list, right? So M signifies a list or an option. This is the element type of the list, right? So it's an integer or something. And then you need to define two functions. Unit, which takes element type like an integer and gives you a list, or takes element type integer and gives you sum of integer. In Haskell, it's called lift, but whatever. And the flat map function, sometimes called sequ function or sequencing function, it's what it does is, well, if you know what it does in lists, but generally, let's think of it for a second. So you have A and B, right, which are two types. You have a list of A, or option, or whatever, right? And you have a function which maps elements of list of A, or whatever, to another list. But in the result, you don't want to get M of B, but you want to get just M of B, right? It's not a map, it's a flat map. And for this reason, like if you define these two functions and they follow certain constraints, algebraic, then you can use it in the for comprehension and magic will happen. Unicorns will arrive. Unicows, right? So here are the monad laws. I do not want to bother you with them, but really the only interesting one is associativity, and it basically this thing is Haskell notation, but it denotes flat map, right? And all it says is that you can move brackets around, right? Here the brackets are right like that, and here the brackets are shifted. It's like if you ever remember algebra from university, then associativity means you can move brackets around. Again, you don't have to memorize it. You can. There are long texts on internet explaining you what all this means and the deep implications. And it all sounds very cool, but frankly, monads are really easy if you don't think too much. Maybe even life is very easy if you don't think too much, but I have never tried, so. So I'll just give you very simple examples. So a list monad. So unit of A, well, is a list A. And a flat map of a list to which we apply a function which returns a list of B, right? Well, we take the list, we apply map, we get a list of B. And then, well, I was a lazy boy and didn't write it out, but there is a function flatten which, well, takes two lists and concatenates them basically efficiently. And voila, we have a list monad. It's actually much more complicated in Scala code because they like many levels of abstraction, but basically that's how it works. And the option monad is, again, well, the unit, we take A and make it sum of A. And the flat map function is even simpler, so we match on this opt, which is the parameter, right, option of A. If it's sum of A, we apply F and get option B. Trivial, right? And if it's none, then there is no point in continuing the computation. We just abort it and return none. And yeah, it sounds very easy. Like for real monads, it's much harder. But you know, here's the concept. Yeah. So actually, like there are also fancy things like monad transformers. So you can apply a continuation monad transformer to a state monad transformer to something else. please don't use them. I mean, like, again, if you have a team of people who really understands this stuff, like, you have 5 superstars from some top university who want to write in Haskell. By the way, Haskell has really good green threads, and it's actually a pretty good language by now. Go ahead, do it. But if you have to hire from less stellar pool of people, I mean, you'll just kill yourself. So we covered kind of advanced Scala concepts. So that's the next level of enlightenment. So we talked about implicits, implicit parameters, implicit conversions, extension methods, type classes, aka ad hoc polymorphism, aka monkey patching your classes, for comprehensions and monads. But there's more. There are very advanced Scala concepts, and now, like, I personally, like, I can probably, so right now I'm somewhere here, and at the level of enlightenment I can understand it, but I probably wouldn't trust me writing this code. Probably when I get here I can get this suit on and say Luke and so on. Anyways, the idea is that, well, I actually invented the term algebra-based programming right now, but the idea is that, like, if you do distributed computations, it's actually really helpful when your elements, your types, have certain algebraic properties, like commutativity, if you remember what it is. Commutativity is that A plus B equals B plus A. And it actually really helps when you try to, I don't know, aggregate lots of data across multiple machines. And there is actually a library called Algebra, which is used by Twitter. And apparently hyperloglog is also a monoid or something. I used to know these names, they're very cool. Anyways, you should know your algebra. It's too late for you, right? You're out of university, but maybe your children or something. Also tell them to learn Haskell or Lisp. I mean, again, it's probably too late for us. I also, like, until 25 thought that functional programming is weird and meaningless and variables are cool. Yeah. Anyways, category theory-based programming. So, functors, monads, Kleisli arrows, applicative functors. It's actually, like, conceivably I could use them, but again, I would have to seriously think if, I can hire a large enough team who can understand this. Because at some point you will have to understand what happens inside, because, like, there is some error or, like, something doesn't work, and then you look inside and they use Unicode characters to denote Greek letters for operator names, and you think, okay. Yeah, so generic programming is actually pretty cool. What you can do is you can write code which is at compile time polymorphing in the types you have defined. So you define a bunch of case classes, and you can write code which is doing something with like case classes of varying types and sizes at compile time. So for instance, this way you can generate protocols or formats for your case classes. So there is also type level programming. So apparently you can do any kind of computation at compile time using Scala type system. Again, if you're doing that in real projects, you should seriously question your sanity. But there are use cases where it's useful because it allows you to express constraints on the types on your functions, which sometimes is useful in the libraries. But it's like, again, like if you have a light subbrand, so maybe it will work for you. And yeah, so there are a couple of meta programming projects which allow you to really, you get the full, like you can apply a macro to a full AST of your code, and you can do basically anything with that code at compile time. And there are a couple of projects like Scala, Reflect, and Meta, and you can do everything you want with it. I think also what usually happens is that people try to use implicits for a very long time to do all this kung fu, and then they say, come on, let's just rewrite the code in Meta or macros. Again, there are some pluses and minuses. All right, so Scala Libraries, let's see how much time I've got for my circus. So like I said, Scala is very good for writing frameworks, DSLs, and so on. So async is a very simple library which allows you to write asynchronous event handlers even more in a more pleasant way than futures or for comprehensions. You just mark as, let's say you can write sequential code, but you can mark asynchronous parts with async statement, and that's it. Like, it will be rewritten into callbacks just by the compiler. There are some limitations to that, and there used to be even fancier thing called continuation passing style. Does anybody know what it is? Yes. Anyways, they don't support it anymore, but basically it could you could write arbitrary Scala code with the blocking statements, and the compiler rewrote it for you into callbacks. Which is like, you know, if it were done well inside the language, would be pretty cool, but as an add-on, it basically at some point died. How many of you ever had to parse a grammar, context-free grammar or something? Okay, the guy in the blue shirt. All right, so like what you usually do, you specify a grammar, some production rules, and so on. So in Scala, you can do it inside the language. So you can basically define your case classes, which represent your abstract syntax tree, and then you just write the productions, like, you know, expression is either a plus b or so on. And this will actually like work reasonably efficiently as a parser of your context-free grammar. And actually, it's more powerful than context-free grammar because you can evaluate expressions at the time of parsing to direct your parsing direction and so on. It's pretty cool. Of course, with all high-level abstractions, like it makes you more productive, but your code is less efficient. So like if you have to do it very much in the production, it probably makes sense to write it by hand. Like as far as I know, most real compilers don't use parser generators, which was a big surprise to me out of university. They actually write all their parsers by hand, at least they used to. So definitely, like Scala compiler, Scala parser generator is not the most efficient in the world, but it's pretty cool. So Scala Check we talked about. This is this random property-based testing of programs or functions. Again, algebra that I actually mentioned. This is this algebraic structures which allow you to do efficient computations across multiple machines. Hyperlog is one of them, for instance. So scalas and cuts are this category-based library with Unicode symbols, with functors and monads and applicative functors and stuff. Shapeless is the generic programming library, and Spire is, if you know NumPy in Python, then it's a bit similar. So, but it actually also it can generate specialized codes for different types, like float and double and so on. As you can see, there's a bunch of projects which are written in Scala. Surprisingly or not surprisingly, they are mostly about data processing. We talked about Slick today already, right? It's functional relational mapping. There is Akka, which is an actor-based reactive programming toolkit, which we talked about last time. It's a bit like Erlang, or I would say Go, Erlang, and Akka have a common ancestor conceptually. So Finagle is some kind of fault-tolerant protocol-agnostic RPC system from Twitter, if I'm not mistaken. So it's a bit in the same space like Akka and microservices, but not quite. I have never used it, so if somebody has used it, maybe we can share your experience someday. Of the interesting things, so Play framework apparently is written in Scala. I learned today it definitely has a Scala interface. A couple of, let's say, cluster computation frameworks, Scalding, which you can basically write Scala expressions which compile to map-reduce jobs. Spark is completely, how many people know what Spark is? Yeah, so it's written in Scala, and you can, let's say, essentially you kind of have collections, like lists and maps and so on, but they are actually running in your cluster. They are partitioned, something called RDD, Resilient Distributed Data Set. And you kind of work with collections, but actually it all happens in the cluster on multiple machines in RAM, which is pretty cool, I think. So I think Martin Odersky calls it the killer app for Scala, Spark. So Kafka, well, it's basically a very efficient event log, transaction log based, event log. That didn't go out very well, but I think you understood what I meant. Basically, you can send lots of messages there, and then you can read it from it. And it's used a lot in LinkedIn, and it was developed in LinkedIn. And there is Samza, which is a stream processing framework, which is again very efficient. What it does is that it reads stuff from Kafka partitions, and it updates in memory key value store. for that reason, it's very efficient, low latency, and it also is written in Scala. So these are very typical places where you would use Scala. As you see, there are no front-end frameworks here, for obvious reason. So I'll just reiterate what was said before earlier. So Scala advantages, well, Scala is basically a gateway drug for functional programming. For people who have a good Java experience and who still use variables, you can treat Scala as Java with prettier syntax and then slowly learn more features. It runs on JVM, integrates with various libraries. Pretty much, usually, it's very easy to do. I would say, if you know what you're doing, it gives you higher productivity and you make less bugs. Also, you write less lines of code thanks to type system and type inference. And, well, I said it many times, it's very good for data processing, concurrent, distributed programming, libraries, DSLs, and writing Scala compilers. So that's how development in Scala looks like. That's a typical day in our office. Yes, we're hiring. On a more serious note, Scala does have downsides. So some call it a modern C++, right? So you try to take a very complicated type system and you shoehorn it into the JVM and the class files. So it's like, you take this magic C++ type system and you shoehorn it into poor C. It has a slowish compile time, although it got much better, and it's incremental. So if you change view files, then the incremental compile time is pretty small. And well, it actually forces you to create smaller projects and generate jars from them, which is a pretty good thing to do anyway. So the interesting thing is that it actually is brittle across Scala and library versions. So typically, your jar will contain the version of Scala and the version of the library. And you will have to compile your code against the specific jar with specific versions. And that's basically because Scala does, it can compile to bytecode, it's all great, but like lots of Scala type system features, like traits with all the magic, do not really have any kind of corresponding stuff in the Java type system or class files. And for this reason, well, that's how it is. So in practice, I don't think it's a big problem, but you have to know that. So some people have a compulsion to use all Scala features, and probably I'm one of them. So please don't do that. Like, it's a very big and complicated language. You can start with a small subset and then go further. It definitely doesn't prevent you from writing write-only code. Like if you overload all your operators with some Perl-like I don't know, slash, asterisk, and colon, then you will never understand what happens. Sometimes libraries and DSLs can have cryptic operators, names or types, and so if you have a compilation error, you will have to understand what happens in the type system. So kind of, the idea is that library developers should write your library and then it's easy to use, and as long as it compiles, it is easy to use. But in some corner cases, you'll spend half an hour basically being a compiler yourself, trying to understand what the error message really means. So you get used to that. Actually, for me, it's not a problem at all. I usually can very easily fix the problem, but it takes time to learn. Yeah, so any kind of higher level abstraction forces you to, well, let's say it gives you overhead. So in practice, your inner loop, the most efficient inner loop of your program probably will be written with a while statement and a var. So mutable variables, old school. But all the other stuff, which is not as performance critical, can be written using these more productive constructs. And they say that tooling got much better lately, although I personally use VI, so I couldn't care less. But apparently IntelliJ works and so on. So probably refactorings will never happen in Scala, but again, grep said, and that's what I use. And maybe a more cultural issue is that it allows you to develop in very different types of programming style, and you will have to understand what kind of people you have, what kind of people you can hire, and you will have to enforce coding standards. Like if every person writes in a different style, well, you have a problem. And yeah, so that's my last slide. with great power comes great responsibility. So, Scala is a powerful tool, but you will have to, think what you're doing. So it gives you lots of opportunities to cut off your legs with light Sabra and so on. And that's pretty much it. So any questions? So I talked you to death, basically, right? All right.
So you said about hiring. So, and like you said you're hiring today. How do you hire then Scala developers? Like, you have to train them all in?
Yeah, basically, yes. I mean,
from Python, from...
It helps if they know Scala, right? But, man, you really... Scala is, you can hire for enthusiasm, right? And intelligence. But, like, what language they programmed before, it's like secondary.
I have a question. You mentioned that Scala allow you to write in a lot of different ways and different styles. So, and probably to enforce everyone write in the same way, you need some kind of person who is like a Scala architect or someone who could, some kind of bad cop who could see it. Where did you get the first person who was with a good experience and such kind of bad cop who could enforce you to write in a specific way?
Do you need a general answer or a specific answer?
Actually, I need a specific answer because I used to work in a project and we had like all of these types in our projects and it was like, what? All the time, so...
So I was the bad cop, but I'm too good person, yes.
So can you modularize? Can you keep different teams working at different levels, or like how you can't just
definitely.
say like the lower denominator and that's it?
So what happens is that typically you write your reusable code maybe here. If you really write a library and framework, you do it here, and hopefully your business logic will be written with that. And maybe less important code can be written with that, and then slowly changed if you have unit tests. I mean, there are very many different creative ways to screw up your project. And like, if you, it's not the only thing you have to enforce, right? They can do other stupid things.
I have a question, Oleg, about lenses. Have you used that? What your experience, impression? Yeah.
Nope. Can you share yours?
Well, mine is, if we talk about the domain-driven design, if we want to avoid nested coping, of the nested case classes, fields, a lot of that stuff. So it's pretty useful.
Okay, cool.
Yeah.
How many years of experience do you have with Scala?
Well, I played with it a long time ago. Then I did some small project, and I did a larger project. Like sequentially all together. Maybe if you add up, maybe 2 years. I went to Chalmers, which is a Swedish school where they wrote the first optimizing Haskell compiler. And I spent 2 quarters playing with Haskell.
Actually, I have one more question. You mentioned cats and Scala Z. Do you use them?
Nope.
Okay.
I could use them, but I don't.
At which point do you can you say that you're proficient enough in Scala to not write like bad stuff?
So the problem is there is this Donner-Kruger effect or something, right? So people who don't know what they are doing think they do, and people who know what they're doing think they don't. So subjectively, it's very hard to tell, right? I don't know where I am on this curve right now. But usually every 5 years you discover that 5 years ago you were very stupid, although you thought you were very smart. So.
That's it. Thank you. Give a round of applause.